Hello everyone. Today I would like to talk about Fischer esterification and its mechanism. But before I get to the arrows and electron pushing, I want to first talk about what the reaction is and what its real-world applications are. And so this is an example of Fischer esterification. Here I have propanoic acid reacting with ethan-1-ol, commonly known as ethanol, forming ethyl propanoate in the presence of a catalytic amount of an inorganic strong acid. And so in general, you have a carboxylic acid, propanoic acid, you have an alcohol, ethanol, reacting to form ethyl propanoate, a carboxylic ester, and in this reaction you have water as a byproduct. And so here's just a color-coded version of the previous slide. And the purpose of this color coding is so you can really see how the carbon count changes throughout the reaction, where you have a 3-carbon reactant and a 2-carbon reactant forming a 5-carbon product, and so you can see how the bonds are formed. One thing I will note, though, is that the color coding is imperfect in one way. The blue carbon-oxygen bond can be formed from the blue carbon-oxygen in the reactants, but that's not always the case. It can also be formed from this pink carbon-oxygen. And that might sound a little confusing right now, but when I go through the mechanism, it'll all make sense. And so this is just another way of showing what I had on the previous slide. You have a carb acid and an alcohol combining to form an ester. You can see these R groups on the reactants. These R groups can really be anything you want. They can be methyl, ethyl, propyl, and they don't have to be the same on the carb acid and the alcohol. So your carb acid could have ethyl and your alcohol could have methyl, or they could both be methyl, for example. It really doesn't matter. And so what that means is that this can be R prime, and that this can be R prime. And if you've really been paying attention, you might have noticed that this reaction is reversible. And so what that means is that if you take this carboxylic ester and expose it to acid and water, it'll actually reform the starting materials, which will be a carboxylic acid and an alcohol. Sometimes when I'm learning reactions, I like to imagine doing them in the lab. In this regard, Fischer esterification is quite simple. All you need to do is obtain a round bottom flask, add your carb acid to it, propanoic acid in this example, add your alcohol to it, ethanol in this example, and just a little bit catalytic amounts of a strong inorganic acid like sulfuric acid. So you've gotten your round bottom flask, you put your propanoic acid in it, then you put your ethanol in it, and then you just put some drops, like just drops, of your catalytic sulfuric acid. And so now you have your mixture of all your reactants, and you need them to react. And so to do that, you apply heat to the system. That can be done using a reflux condenser. That will allow you to apply heat to the system for a long time while preventing evaporation of the reaction mixture. And so you would put in the reflux condenser, heat it until the reaction is completed. I've shown that with a color change here. And then you would need to isolate your product, the carboxylic ester. And so you can isolate the product using a separatory funnel and extraction. Since your product is an ester, it will be in the organic layer. And so you would do an extraction, isolate the organic layer, and then you need to dry the organic layer, and that can be used with a Pasteur pipette and drying column. And so once you've dried your organic layer, then the last step, the final step, is that you put it on the rotovap, and then you get some solid organic carboxylic ester product. And so the reaction is really as simple as it's written. You're getting alcohol, you're getting carb acid, you're mixing them up and reacting them, and then you just get your ester out. So now that you've seen the reaction for esterification, you might be wondering, what's the point? Why would we want to make esters? Well, esters have a lot of really important and valuable uses in our daily lives. For example, the ester methyl acetate is an important component of glue. I'm sure you've all used and benefited from glue before, and that's in part possible because of esterification. But esters really get their fame from their role in creating the odors in fruit. For example, pears get their smell from the ester propyl acetate. In apples, you'll find ethyl isovalerate, and that gives them their distinctive smell. And methyl cinnamate produces the smell in strawberries. And so scientists have taken advantage of the odors esters can produce in the food production process. Pictured on the screen is pear drops. These are a common candy in the UK, and as you might guess from the name, they taste like pears. Let's take a closer look at the ingredients to see where they get this pear flavor from. So you'll see sugar, glucose syrup, citric acid, and then flavoring. What's this flavoring? Well, in pear drops, it's isoamyl acetate and ethyl acetate. These are the two esters that actually give pear drops that pear-like smell and flavor. Okay, and so let's get back to reactions. We'll be working through the mechanism of the same reaction I showed on the first slide, propanoic acid with ethanol reacting to form ethyl propanoate. And so now let's work through the mechanism of this esterification. The first step is the protonation of the carbonyl oxygen, done by H+. H+ comes from the H2SO4 in the reaction, the catalytic sulfuric acid. And so the protonation can be shown like this. And so now this protonation has really strong effects on the structure. The carbonyl oxygen is now positively charged. And since it's positively charged, it can more strongly draw in negative electrons. And so what that means is that the carbonyl carbon is now more electrophilic. And that allows our ethanol in solution. Ethanol is usually a weak nucleophile. It has a neutral oxygen. It allows that ethanol to attack the carbonyl carbon, which can be shown like this. And the carbonyl carbon, to avoid pentavalency, will just kick up some electrons, forming a hydroxyl group with this structure here. That step was called nucleophilic acyl substitution. And this is the resulting structure. Here the oxygen has a positive charge, and what that allows for is an intermolecular proton transfer called tautomerism. And so the way that will work is one of these OH groups, either one, they're identical, can attack that H, leading to this structure here. And this attack by either OH is the thing I was referring to when I was discussing the color coding of the reaction diagram. And so next, you can have an elimination. With that intermolecular proton transfer, you created an H3O+, which is a very strong leaving group. And this OH, it can easily reform a carbonyl since carbonyls are so stable. And so this elimination can be shown like this. And that H3O+ will leave and form that water leaving group we like. And then this structure will result. And now here we again have an oxygen with a positive charge, and in this case some conjugate base can come in. It will be our HSO4- coming from the catalytic sulfuric acid, and it can attack that hydrogen, allowing our oxygen to be neutral again. And so the final structure we'll have will be this, with water as a byproduct. And here's just a neat version of the mechanism on the previous slide. I'm really just putting this here as a study tool you can use for yourself. And now a practice problem. This is actually the synthesis of methyl cinnamate, which I discussed has a strawberry-like scent. So pause the video, try the problem out, and then I'll discuss the solution. Alright, so let's work through the solution. Carbonyl oxygen first gets protonated. That makes the carbonyl carbon super electrophilic, allowing for our methanol to complete a nucleophilic acyl substitution. That forms the resulting structure here. This one will undergo a tautomerism, intermolecular proton transfer, and same as before, either OH can do the attacking, which will form this resulting structure, which will undergo an elimination, right? So you'll have your H3O+ leave, and the OH reform a carbonyl group. And so the structure that forms from that will look like this, and it'll have an oxygen with a positive charge, which can easily be deprotonated by the conjugate base we have, which will be HSO4- coming from the catalytic sulfuric acid. And then we'll have our final structure, methyl cinnamate, with water as its byproduct. So again, I've just drawn the mechanism a little bit neater here so you can study it on your own and really understand it. And so that's the tutorial. That's Fischer esterification. Thank you for watching.